So this question is from the 2017 exam. Some of the things are AB related and some are BC related. So while the question was on the BC exam, Part A is AB material, Part B is AB material, and then Part C is actually BC content. And there is a Part D that I removed for our test. In the video I will get to it, but it wasn't part of our test that we did. It has to do with sequences and series. So Part A is find the slope of the line tangent at x equals 3. So Part A is very simply asking you to find f prime of 3. That's what they're asking us to do. Given the fact that our function is a quotient, some of us might be inclined to use the quotient rule, which is completely acceptable, but I think that it is easier to write this as a chain and power rule. So when we take the derivative of this function, we get negative 3 2x squared minus 7x plus 5 to the negative 2 times the derivative of the inside. So f prime of x is negative 3 4x minus 7 2x squared minus 7x plus 5 squared, and we evaluate that at 3. So f prime of 3, if we plug 3 in, would come to negative 15/4. The grading for this portion of the test was worth, it says 2 points for finding f prime of 3. So I think the graders were very much either you get f prime of 3 correct or you do not. Moving on to Part B, it says find the x-coordinate of each critical point, and we know critical points or critical values occur when f prime of x equals 0 or f prime of x does not exist. So in order to find our critical points, we're going to look for that location. Now we've already established that f prime of x is negative 3 times 4x minus 7, 2x squared minus 7x plus 5. So we're asking the question, when does this equal 0? So there is going to be a critical value, this equals 0, at x equals 7/4. Oops, I forgot the square there. Okay. If we were to factor the denominator, 2x plus 2x minus 5, 2x minus 5 times x minus 1, that value is squared. So there are critical values also at x equals 1 and x equals 5/2, but on the question they want us to not include the boundaries of 1 and 5/2. So those are outside the interval. So we're only going to examine the critical value at 7/4. And we want to determine whether this is a maximum, a minimum, or neither. So if we do the first derivative number line at 7/4 and we choose numbers on each side of 7/4, f prime changes from positive to negative on each side of 7/4. So there exists a local max at x equals 7/4 because f prime of x changes positive to negative. So that's using the first derivative test for local extrema. It is possible to use the second derivative test if you wanted to find the second derivative of this. However, that's a pretty nasty thing to do a second derivative for. So the points come from 1, did you find the critical value? And 2, did you conclude a maximum with a justification? So those 2 points come from those 2 locations. Okay, Part C, they actually ask us to evaluate the improper integral of this. And fortunately for us, they were kind and they did the partial fraction decomposition for us. If we did not have the partial fraction decomp done, we would have used probably the Heaviside cover-up method. But they want us to evaluate from 5 to infinity of f of x. Now this improper integral has improperness because the upper bound is infinity, and we know that we can't have infinity in the upper bound. So by rewriting this as a limit expression, we are turning this into a evaluatable expression. When we find the antiderivative of each of these pieces, the antiderivative of this, 2 from the numerator, constants go along for the ride, times 1/2 ln of the absolute value 2x minus 5, subtract ln of the absolute value of x minus 1, evaluated from 5 to b, and we're going to be taking the limit of that expression. Now, it is probable that several people forgot this 1/2 here. Remember, the u substitution that we do on the denominator is going to cause that adjustment of the 1/2 there. Okay, cleaning this up before we get to the part of evaluations, the 2 and the 1/2 cancel, ln, and then the subtraction using log properties, we have 2x minus 5 over x minus 1. And at this point, the absolute value can be dropped because for all numbers in the interval 5 to infinity, those arguments would be positive. So the absolute value is not necessary at this point anymore. If we go from 5 to b, this gives us the limit expression of ln of 2b minus 5 over b minus 1, subtract ln of 5 over 4. When we evaluate this limit expression, the numerator and the denominator are growing at the same rate, and so we can pull this limit inside, and the limit evaluates to ln of 2 minus ln of 5/4, and that is a finite number. So this improper integral converges to this finite value. The 3-point breakdown comes from 1 point for the antiderivatives. So if you got the antiderivative correct, that's going to be 1 point. Did you remember to include the limit expression? That is worth 1 point. And then finally, did you arrive at the correct solution? That is your third and final point. So that's 7 out of the 9 points. The last 2 points comes from part D, which I'll record, but we didn't do on the test. So. All right, finally, moving on to part D of the question from 2017. We are determining whether the series converges or diverges. It wants us to state the conditions of the test used for determining convergence or divergence. And if you'll notice, the series they're questioning is closely related to the equation that we had been exploring, the function. So there's actually some value into that, because in part C we used the improper integral to determine convergence or divergence. So there's probably parallels between the improper integral and the series. Or not probably, there is. So if we use the integral test, so the integral test for convergence or divergence, we're going to determine whether this series converges or diverges. And the integral test says that if we were to map this rule of sequence onto a function, which it does, and if f of x is continuous, positive, and decreasing, then either the improper integral that we had done from 5 to infinity is convergent. I guess we should say and this improper integral is convergent. Therefore, the series from n equals 5 to infinity also converges. Now, it should be noted that we haven't shown explicitly that f of x is continuous, positive, and decreasing. So if we look at our original function, it factored the denominator had discontinuities, there were discontinuities because the denominator equaled 0 at 5/2 and at 1. But after the value of 5, this function is continuous. Furthermore, if we look at the value after 2.5, we saw that the derivative was negative, and so that's our support for why we know that the function is decreasing. Finally, we just need to determine that the function is positive, and if we do some sign analysis, we see that the top is positive, and if our input is any number greater than 5, the denominator is also positive. So all three of these things are met, so we can run the integral test. The integral test, as a reminder, says that if f of x is continuous, positive, and decreasing, and the improper integral is convergent, then the series is also convergent. Furthermore, if the improper integral is divergent, then the series would also be divergent. Now, that is not the only test that you can use to prove the convergence or divergence of this series. We could do a limit comparison test that would work as well, so I'm going to show that down here. This is just an alternative approach to showing convergence for the series of this expression. So first off, we have the expression, which we've established as positive, as well as another expression, which is positive, and that's going to be for all n greater than or equal to 5, which our series is focused on, so all we have to do is care about past 5. This is a convergent p-series, and we're testing this one. I'll write that in here, convergent p-series, p equals 2, which is greater than 1. Okay. So for the limit comparison test, if we take the limit as n goes to infinity of the one that we are testing over the one that we know something about, we get a limit value of 3/2, which is positive and finite. So because this is positive and finite, and we know that this converges, then by the limit comparison test, the series for this expression also converges. So therefore, 3 over 2n squared minus 7n plus 5. Also converges by the limit comparison test.